Hello everybody, welcome to this course on modeling, analysis and estimation of three-phase unbalanced power network. The purpose of this course is to analyze the unbalanced power network. In this course specifically, we will not be talking about any balanced network because that analysis has already been carried out in another course on computer aided power system analysis. The reason for this course is that due to the introduction of several renewable energy sources in our system, as well as let us say electrical vehicles, the unbalance in the power network is continuously increasing. So, therefore, although so far we have been assuming that our system is actually operating on a balanced manner, but then in future probably this will not be so very rigorously. So then therefore it is actually needed to understand that how to analyze a system in its total unbalanced operation. Now we need to remember that in the case of distribution system we do always adopt an unbalanced approach for its analysis. But for the transmission network, we generally assume that the transmission network is usually balanced. That is essentially the parameters of this network is balanced and as well as the loading at every phase of that network is also balanced. But because of the introduction of several renewable energy sources, electric vehicles and the other power electronic loads and etc., 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 at the interface of the transmission and the distribution network, this may not be true. So, essentially that is the purpose of this course, to understand that how to analyze a transmission network when it is operating in an unbalanced manner. In this course, we will not be talking much about the distribution system operation and analysis because for that also some other NPTEL course has already been designed by some other colleagues. So then therefore this course is more or less mostly geared towards the analysis of an large transmission network when if it is operating on an unbalanced system. Now this course has got essentially 5 modules. First module is the calculation of the inductance of an unbalanced transmission network. Second module would be the calculation of the capacitance of an unbalanced transmission network. When we are talking about the inductance of the transmission network, we are actually talking about the impedance matrix, because for any unbalanced transmission network, the inductance or the capacitance won't be a scalar quantity, but rather they would be a 3 cross 3 matrix. So then therefore we will be looking into the case that depending upon the configuration of the network, how to calculate the impedance matrix, that is the inductance matrix as well as the capacitive matrix. Once that is done, after that we would be talking about the modeling of transformers. Now, when we are talking about the modeling of transformers, we are talking about the 3-phase modeling of the transformers, and for 3-phase modeling of the transformers, we have to consider the vector group of the transformers. For example, if I have a 3-phase transformer, for example star star, and if the vector group is say star star 8, so then we will look into that how to model this 3-phase star star 8 transformer for our load flow analysis. Once that is done, then we will look into that how to incorporate the models of the transmission line inductance as well as the transmission line capacitance and also of the 3-phase transformers, various vector groups, that is how to include all these models for developing the Y bus matrix of the transmission network three phase unbalanced transmission network. And once that is done, after that we will be looking into the power flow equations, and from there on we will be looking into that how to solve those equations. So essentially we would be talking about the Jacobian matrices and then the standard mismatch equations, solution vectors, and how to solve them. All these things we shall be looking into in very detail. So hopefully by the completion of this module 4 or maybe 3, we would be able to understand very clearly that how to go about doing the power flow analysis of an unbalanced transmission network. Once that is done, then we shall be talking about that how to perform three phase state estimation. Now, when we will be talking about this three phase state estimation, now that particular technique is not really very specific to any transmission network. That particular technique is also equally applicable to a three phase unbalanced distribution network. So then therefore, the technique for three phase state estimation would be actually common for both transmission network as well as the distribution network. On the other hand, the technique for unbalanced load flow analysis of a transmission network would be only specific to the analysis of an transmission network. That particular technique per se is not very much applicable for the analysis of an unbalanced radial distribution network. So, this is the outline of this course. For this course, we shall be following 3-4 books. We will be mentioning those books as and when it is required. So, with this very small introduction, let us now start our actual discussion of the course. So, in that we will first now talk about the parallel cylindrical wire of finite length. Actually, we are talking about the inductance of the parallel cylindrical wire of finite length. So, I should write that inductance of a parallel cylindrical wire of finite length. So, what we have is that we know that the inductance is essentially defined as the total flux linkage W say 1 divided by I. So, Wi by Ii. Wii is the flux linkage, is the flux linkage of ith wire. Please note here we are only talking about only one wire. So, then therefore, here I is equal to 1, but then we are actually following this particular notation to make it more general, and Ii is the current through the Now, we know that the total flux linkage is actually constituting of the internal flux linkage and the external flux linkage. Now, due to this internal flux linkage, so then therefore, we will have one inductance which is basically caused by this internal flux linkage. So, we will call it by inductance due to the internal flux linkage, and then we will also have another inductance which is caused by the external flux linkage, which is actually linked to this particular conductor externally. So, then therefore, I can say that L is actually Li plus Le. Now, here there is one abuse of notation. This I is internal flux linkage, internal inductance. So, here I think I should, what I do is, instead of using this I should use 1, otherwise it is causing problem. So, it is, let us say W11 I1 of the first wire. So, I can write it is as of the wire. So, it is internal inductance, it is due to internal flux linkage, and LE is the external inductance due to external flux linkage. So, then therefore, what we have to do? We have to essentially find out the expressions of Li and Le, and then we have to just add them up. Now, we know that from our basic uh, basic third year, or let us say second year course, that is essentially from our BTech course, we know that Li would be given as mu by mu s by 8 pi Henry. Now, here mu is, we know that 4 into 10 to the power minus 7 Henry per meter standard. S is the length of the wire. Please note, here we are not talking about, in this course we are not talking about a long cylindrical wire. We are not talking about the long cylindrical wire. We are talking about a wire which is of finite length, because in reality any transmission line, or let us say any line for that matter, is of finite length. So, then therefore, here in this course we always be talking about any finite length line. So, length of the wire in meter or kilometer, let us say meter, and 8 pi is 8 pi. Now, for LE, we have to first find out that what is the expression of lambda E. Now, what is lambda E? So, now first we have to find out that what is the expression of lambda E. Now, to find out LE, we have to first find out lambda E. What is lambda E? Lambda is the external flux linkage. We have to first find out the expression of lambda E, and from that lambda E we would be able to find out LE. Now, the expression of lambda E, I am not going into the derivation of this. This is given by mu I1 by 2 pi into S log S plus root over square plus R square by R minus square plus R square plus R. This is Weber turn. Now, here of course, this expression looks to be pretty complicated, and one may wonder that from where this expression comes. Now, essentially the derivation of this expression is quite involved. So, we are actually avoiding this for the purpose of this course, but if you are interested, you can look into the following book. The detail for I mean detailed derivation, this book is, I mean one may look into the book of analysis of faulted power system by P. M. Anderson, and it is a little old book, some 50 years old, Iowa State University Press, but it is a fantastic book. Iowa State University Press and 1976 edition. I have that copy, 1976 edition. So, if anybody is interested, it is given in that book. I think it is an appendix D of that book. It is a long derivation, some involving some, I think 2 pages. So, for the sake of avoiding unnecessary details, I am just avoiding those particular long derivation, because that derivation is not necessary for us. What is necessary for us is the expression of this external flux linkage. Now, here of course, another thing I should have mentioned here, r is of course the radius of the, r is, and r is the radius of the conductor, right. So, r is radius of the conductor, and s we have already said that s is length of the conductor. So, if this is meter, so then therefore this is also in meter, and mu is we have already defined, 4 into it is a constant, and I1 we have already defined that current through the wire, it is I1. I should write, sorry, it should be lambda 1 I1. So, notations must be, so it is I1. So, current through the wire, so this I1 is this one and 2 pi is a constant. So, this is it. Now, what happens? Usually R is very much less, usually R is very much less as compared to S. So, then therefore, if we look at this expression, R is very much less. So, then therefore, in this expression R is negligible. So, then therefore, only root over S square will be there. So, then therefore, root over S square is nothing but S. So, it is S plus S 2S by R, of course, we cannot neglect that. And here is also S square plus R square would be approximately equal to root over S square, that is S, and this R is very negligible. So, then therefore, this entire expression will be reducing to, now for we can write down lambda E would be reducing to mu I1 by 8 pi S log twice S by R minus S, right. So, then therefore, I can, what is happening? So, then therefore, I can write down it is as take S common, mu I1 into S by 8 pi, take S common, log twice S minus R by 1. So, then therefore, LE would be equal to lambda E by I1 is equal to mu S by 8 pi into log twice S by R minus 1. So, this is the expression of external inductance. So, then therefore, my total inductance L would be Li plus Le. So, Li plus Le would be equal to, now what is Li? Li is, we have already looked into, Li is given by mu s by 8 pi. So, then it would be mu s by 8 pi plus Le is mu s by, sorry, this is not 8 pi, this is wrong. This is not 8, sorry. So, this is actually 2, 2, 2. So, it is 2 pi into log, right. Here is also another writing mistake, it should be, this is 4 pi. So, then therefore, inductance per length is equal to mu by 8 pi plus mu by 2 pi L twice pi r minus 1. So, it is Henry per meter. So, it is Henry per meter. So, then therefore, let us denote it as the total inductance. Here it is per length, per unit length is actually given by mu is 4 pi into 10 to the power minus 7 by 8 pi plus mu is 4 pi into 10 to the power minus 7 by 8 pi into log twice s minus r by 1. So, it is equal to half into 10 to the power minus 7 plus 2 pi, sorry, 2 into 10 to the power minus 7 into log twice s minus 1. So, L, so then therefore, we get L is equal to, as we just now see it, that half into 10 to the power minus 7 plus 2 into 10 to the power minus 7 log 2s minus r minus 1. Now, if I take 2 into 10 to the power minus 7 common, 2 into 10 to the power minus 7 common, I get 1 by 4 plus log twice s by r minus 1. That is what I get. Now, 1 by 4 I can say that now 1 by 4 I can say that log of e to the power 1 by 4 is equal to log of 1 by e to the power minus 1 by 4, right. This ln is nothing but the logarithm with respect to the natural base. So, then therefore, I can write it down as 2 into 10 to the power minus 7, 1 by 4 is log, so it is log 1 by e to the power minus 1 by 4 plus log twice s by r minus 1, right. So, it is 2 into 10 to the power minus 7 into log twice s into r into e to the power minus 1 by 4 minus 1. So, it is 2 into 10 to the power minus 7 into log twice s by, we call it ds minus 1, where ds is equal to r into e to the power minus 1 by 4, it is equal to 0.7789, I think, r. So, we also call it self GMD, right. So, then therefore, the total inductance of any line is given by L is equal to 2 into 10 to the power minus 7 into log twice s by ds minus 1. So, this is the expression of inductance of a cylindrical wire of finite length. So, if it is the inductance of the cylindrical wire of finite length, so then obviously I can say now obviously because this wire has got some length and of course it is also made up by some material. So, then therefore, that material has got some rho, I mean resistivity. So, then obviously that particular wire also has got some resistance. So, then therefore, the impedance would be given by R plus j omega L. Now, here R, now this R and that R will be confusing. So, we should use some other notation. So, let us say RC plus j omega L. RC is the resistance of the conductor. Please note here, please note this R is here the radius, but this R is actually the resistance of the conductor. So, we can even possibly instead of using capital R, we can use capital R. So, this is the resistance of the conductor. So, then therefore, Z would be R into j omega L, where omega is the frequency. So, it is obviously R plus j omega some constant k, k is log twice s by ds minus 1, where k is the constant 2 into 10 to the power minus 7. So, henceforth we shall not be always writing the value of 2 into 10 to the power minus 7 always, to avoid unnecessary repetition we shall be using this constant k. So, then therefore, henceforth when we will be using this value k, we should be able to understand that this value k has got the value of 2 into 10 to the power minus 7. So, this completes the derivation or rather the expression of the inductance of a cylindrical wire of finite length. So, with this background we will now be continuing with the other aspects of the course. Thank you very much.